Hello students, welcome back. We will continue our discussion on the use of Maxwell's relations in thermodynamic systems. And today we are going to discuss some simple numerical and conceptual problems where we use Maxwell's relations. So, the topic of the class today is using Maxwell's relations to solve problems. Now, let me remind you that we actually derived these 4 sets of relations which are known as Maxwell's relations, and we used here the mnemonic sportive. And we also showed that the utility of Maxwell's equations is to correlate the variation of energy functions with temperature, pressure or volume with measurable properties like specific heat, which is Cp and Cv, coefficient of isobaric expansion alpha, and the coefficient of isothermal compression kappa. And we have seen that these are the equations which are the thermodynamic equations for the energy functions U, H, and also for the entropic functions S under constant temperature volume and constant temperature and pressure, which can be expressed entirely in terms of these response functions. And we have also discussed what happens if I work with 1 mole of an ideal gas, a monatomic ideal gas, for which we know that the ideal gas equation tells me that the pressure into volume is equal to RT, and from the kinetic theory of gases we know that the internal energy is given by 3/2 into RT. And then it is possible to find out the different response functions as listed over here, and then I can actually calculate the values of these response functions for an ideal gas as mentioned over here. Now, moving ahead, I have to keep these points in mind when I solve the numerical problems. Now, these numerical problems, depending on the kind of problem that you are handling, may be a very simple extension of the Maxwell's relations. So, let us have a look at this first problem where the question given is as follows. Show that the variation of entropy with respect to volume under isothermal condition is equal to this amount for 1 mole of an ideal gas at STP. So, standard temperature and pressure. And therefore, to know the variation, we have to find out the partial derivative of S with respect to V at constant temperature. So, then the question is, where do I start from? You understand that in this case I can use the Maxwell's relation, where it will be possible for me to get del S del V T in a closed system. Now, if I look into the mnemonic, yes, I can find out del S del V T. What will the answer be? The answer is going to be, by Maxwell's relation, this is going to be equal to del P del T V. So, that is exactly what I have written down here. You might want to remember that here, while using this mnemonic, I have executed a vertical step first and then a horizontal step. As a result, there is a plus sign over here in the answer while I write down the Maxwell's relation. So, now I see that the variation of entropy with respect to volume under isothermal condition in a closed system, it is given in terms of the variation of pressure with respect to temperature under isochoric condition in a closed system. Now, this tells me that I can now very easily use the equation of state of an ideal gas, because the equation of state of an ideal gas for 1 mole of it at STP, I must be having P equal to RT divided by Vm. So, what is Vm? Vm is the molar volume of the gas at STP, and then I would be able to write down what is del P del T V. If I keep this volume constant, then del P del T V turns out to be R divided by Vm. So, now I take the value of this derivative from here and put it back in this expression. When I do that, then what I find is I now have del S del V T n, that is equal to R, which is the universal gas constant, divided by the molar volume of the ideal gas at STP. Then it turns out to be that I can write down the numerical value of R, and we also know that the molar volume of an ideal gas at STP is 22.4 liter per mole. As a result, then I can find out that the numerical value is 3.66 into 10 to the power of minus 3 atmosphere per Kelvin. So, this is the answer, and that basically tells me that all I needed to do to solve this problem is realize that this is a quantity that can be directly derived in terms of pressure, temperature, the derivative of pressure with respect to temperature under isochoric condition, that can be directly obtained from Maxwell's relations. But not all problems will be as simple as this. There are other problems where the application of Maxwell's relations require expressing the thermodynamic property in terms of unnatural variables. For instance, let me explain that we know that in terms of the measurable response function ds with changes in temperature and volume can be expressed in terms of Cv dt by T plus alpha by kappa dV. Similarly, for a system whose thermodynamic state is being denoted by temperature and pressure, and if it undergoes an infinitesimal change in state such that its temperature changes from T to T plus dt and pressure changes from P to P plus dP, the associated change in entropy can be directly written down in terms of Cp and alpha. Then the question is, it is understandable that under such circumstances S has its natural variables as T and V or T and P in a closed system, and therefore, I can very quickly write down ds in terms of the specific heat and appropriate specific heat, and then alpha and kappa. But what happens if I have chosen some representation of the thermodynamic state of the system which is not the natural variable? Under such circumstances, there are some common manipulation techniques of calculus that are found to be extremely useful, and I am going to use a discussion from this very nice advanced textbook of thermodynamics, which if you are interested you can look up, and let me give you a table which gives some useful results from partial differential calculus. The first property that I get from here is known as the inversion property of partial differential calculus, and this is as follows. All the thermodynamic quantities that we are dealing with actually follow this particular rule. If I have del x del y keeping z constant, in that case I can write it as inverse of del y del x keeping z constant. And it is very useful to note that we kept on using this kind of relationship all throughout our discussion of thermodynamic properties so far. Now, there is a second one which is known as the triple product rule. Now, when I am writing down the triple product rule, then I am assuming that x is a function of two more variables y and z. Okay? So, I used this relationship del x del y z into del y del z x into del z del x y equal to minus 1. Okay? We have used this extensively when we try to understand the variation of different energy functions like internal energy and enthalpy. Now, although this is most commonly encountered in thermodynamics, there are other properties from partial differential calculus which turn out to be extremely useful when I am dealing with non-natural derivatives of thermodynamic functions. For instance, there may be such situation where I am trying to evaluate this partial differential del y of x keeping z constant, but I do not know x directly in terms of y. Rather, I know x as a function of w, another independent variable, and y too as a function of w. So, in that case, what I do is I can express this partial differentiation into as a ratio of these two terms, and this is the addition of the variable w into the description, keeping the overall constancy of the variable z unchanged. And finally, the other result for non-natural variables turn out to be, if it so happens that you have a function a which has x and y as its independent variables, then obviously dA, the exact differential of a, can be written down like this. Now, I am asking the question from here, can I find out what del a del y z is? Now, please see that there was no z in this particular expression on the right hand side of this expression for the exact differential a. But now, I have to find out what is happening to a when it is varying with the variation of y under the constancy of z. Now, very quickly you can express this, that this is going to be del a del x y, this coefficient remains the same, but now I must be having del x del y, how this variation occurs when z is held constant. Now, you must realize that not all these results are valid for all types of differentials that you come across in mathematics, but by the formulation in thermodynamics, we are fortunate that all these results are perfectly valid for all the state functions that we are going to look at. Now, let me go ahead and see that how I can use this kind of results where a process involves some kind of non-natural variables. So, the first problem that we see in this category is as follows. What will be the change in entropy of a gas upon heating under isenthalpic condition? So, what I am looking for is I am looking for change in entropy, I am looking for heating, which means I am looking at del S del T, because upon heating the temperature will change. So, your experiment is you are heating the system, therefore, how do you know the system is being heated? Its temperature will change. So, your independent variable in this particular experiment is T. As a result of the change in temperature, the entropy is changing. So, the partial derivative that you are going to look for is del S del T. And under what condition are you carrying out the heating? You are carrying out the heating under isenthalpic condition. Now, if by looking at this you immediately think, okay, it is entropy variation. Can I not just go and use the Maxwell's relation? You will find that there is no way you can use the Maxwell's relations directly to solve a problem like this. So, what you would do is, you now try to understand that we need to find del S, del T, H. And in order to do this, what we will do is, I will introduce an additional variable P. So, I am going to write down del S, del T, H is equal to del S, del P, H divided by del T, del P, H. Actually, when I looked at this problem for the first time, I thought about the Joule-Thomson coefficient, because that is the only experiment that we have come across that takes place under isenthalpic condition. So, immediately I can write this down, that the denominator here is the Joule-Thomson coefficient. So, now in order to find out this derivative, I need to know what del S del P H is and what mu j T of that gas is. Now, moving ahead, I am going to use the fundamental equation of thermodynamics that tells me dH is equal to TdS plus VdP. In a closed system, this is the expression that tells you that H has as its natural variable S and P. Therefore, dH depends on ds and dP, and the corresponding coefficients are temperature and the volume of the system. So, from here, if I say that I am going to use an isenthalpic condition, in that case what I will say is, I will put dH equal to 0. So, I must be having this equal to TdS plus VdP. Therefore, under isenthalpic condition, I understand that I must be having TdS equal to minus VdP. And what does it mean? It means that I have this relationship that del S del P H, that must be equal to minus V by T. So, all I have done is, I have just rearranged these two, the two sides of this equation, and I have formulated this del S del P H. I am now going to use this relationship and put it back here. Therefore, what I get now is del S del T H is equal to minus of V by T into the Joule-Thomson coefficient of the gas. We can stop here, because I have got everything that I require to evaluate this change. The slope of the curve, where I am plotting temperature along the x axis, entropy along the y axis under isenthalpic condition. Okay? And at every point of the plot, if you know the value of the temperature, the corresponding volume of the gas and the Joule-Thomson coefficient, you should be able to find out the slope of the curve. But the question is mu j T a property that you always measure? Although charts are available where mu j T is tabulated, sometimes you can actually choose to change mu j T into much more available quantities, that is mu j T you can express in terms of other measurable properties. We have already seen in our previous lecture that mu j T is equal to V by C p into alpha t minus 1. Okay. So, as you see that instead of writing down the Joule-Thomson coefficient, you can invoke in your description the specific heat and the coefficient of isobaric expansion. And if you put this back into this expression, what do you get? I just have to do a little bit of algebra, and then I will get that del S del TH, that is equal to Cp divided by T into 1 minus alpha T. So, that gives me the final expression of a process which is not a standard process, where I am looking at the change in entropy with temperature in terms of measurable response functions like specific heat and coefficient of isobaric expansion, and the temperature at which I am measuring the slope, determining the slope of this curve entirely. So, this brings me to the next problem, which once again is something that will not be easily solvable by direct application of the Maxwell's relations. Now, what is it that I am looking at? I am looking at an isothermal process. So, the isothermal process is a very common process, unlike an isenthalpic process. But what I am looking at is something unusual. During this process, I would like to know the rate of variation of Gibbs free energy with respect to Helmholtz free energy. Okay. So, what is it that I am looking for? I am looking for this partial derivative. I have kept temperature constant, and then I am varying the Helmholtz free energy F, and I am looking for the resultant change in the Gibbs free energy. Now, how do I go about it? Obviously, if you are looking for a formula to work with, it does not help. So, let us start from the scratch. Let us start from the definitions. So, what is the definition of G? Gibbs free energy is given by U minus Ts plus PV. At the same time, I realize that the Helmholtz free energy is U minus Ts. If I put this back in this expression, what do I get? I get that the Gibbs free energy is equal to Helmholtz free energy plus PV. That basically tells me that this equation should be the starting point for me to evaluate this partial differential. Okay. So, let us do that. So, what is del G del F t? So, del G del F t is, first I take a derivative of this first term, obviously that will give you 1. Then the second term will yield del F of PV at constant temperature. Okay. Do not jump into conclusion that this is going to be 0, because I have never said that my system is an ideal gas. So, PV is not equal to RT for any system, it happens only for an ideal gas. So, here I will have to do a generic treatment. If I go further, what I will find is I can take derivative of the two terms P and V. Therefore, the first term gives me V into the derivative with respect to P, and then the second term would be P into derivative with respect to V. Now, here comes the realization that how I am going to evaluate these two rather unnatural looking partial derivatives. I know that F is a function of temperature and volume, okay, and therefore, del F del V t is something that I can find out very easily. And the way I do it is as follows. I say that okay, dF is equal to minus S dt minus P dV. That tells me that del F del V t, that must be equal to minus P. So, I just rearrange and I find that the first derivative, this final term shown in purple, that must be equal to minus 1. So, I put it back up here, and therefore, I get del G del F t, that will be decided by V into del F of P under isothermal condition. So, solution of this problem now amounts to our success in finding out this particular derivative. So, now let us see what we can do about it. So, df is equal to minus s dt minus p dv. Therefore, using the definition, I must say that minus p is equal to del f del vt. Okay? Now, I must also say that I can use the tricks that I have shown you here and write this as del f del pt divided by del v del pt. Now, what happens is, now you see that you have a negative sign, then you have an isothermal condition where pressure is being varied and volume is changing. What does it remind you of? It does remind you of one particular response function, and that is kappa. Therefore, I should be able to write that del f del pt, that is equal to p into v into kappa. So, what is the definition of kappa? You have seen it before. Kappa is equal to minus 1 by v del pt. So, now with this result, what is it that I can do? I needed del p del f t. What is it that I have? I have del f del p t. So, which property from partial differential calculus am I going to use? I am now going to use the inversion property, and when I do this, I get a very simple expression that del g del f t is equal to 1 by p into kappa. So, this brings us to the end of our discussion today regarding the use of Maxwell's relations, and then looking at how to correlate the variation of any thermodynamic property either to measurable properties like specific heat or alpha or kappa. But I have also emphasized that simply looking for an appropriate Maxwell's relation does not always help. You really need to have a look at the kind of process that you are studying, whether the thermodynamic property that you want is given in terms of its natural variables, and if the natural variables are not specified, in those cases you have to use some tricks of calculus to understand how to obtain the variation of some thermodynamic property in terms of other measurable quantities. Thank you.